So here's the explanation on what is a nuclear reactor and how it works. First of all, the size, a nuclear core for a nuclear reactor isn't gigantic. It's about the size of a typical classroom, and then if you took away the ceiling, put another classroom on top, and that's about the size of a nuclear core. Now, think about that classroom, 2 stories tall, and the walls around the classroom or nuclear core would be several feet thick, reinforced concrete and steel. Okay, that's about the size. Next, what they have to do is they have to insert aluminum tubes. They're called fuel rods, and they would go horizontally from one wall to the end of the classroom to the other wall. And in those tubes, they would put the nuclear or the uranium fuel pellets. Okay? Now, these fuel pellets, like we talked about before, one of the fissionable radioisotopes of uranium is uranium-235. But the problem is there's only 0.7% of uranium-235 in all of the uranium. Most of the uranium isotope would be uranium-238. So they have to use something called enriched uranium. So, the fuel for most nuclear reactors. It's called enriched uranium. So instead of putting these fuel pellets, and they look like those little things at the bank, you know, where you put them in and they get sucked up and they go around. They're about like that big. And these uranium fuel pellets are made of enriched uranium, which means it's not 0.7%, it's this. So, the enriched uranium that they use in nuclear reactors is 3% uranium-235. Okay? Now, think about this, because they have sometimes thousands of these aluminum tubes going horizontally through a classroom or a core that's 2 stories high. Okay? Now, so that is the fissionable uranium-235 at 3%. Now, I told you before, they have to have something to slow down the neutrons, because once they come flying out of uranium-235, they're very fast. And they would go right through other uranium-235 nuclei without doing anything. So they have to slow them down. Now, there are 2 ways to slow them down. 2 substances to slow them down. The United States mainly uses something called heavy water. The Russians use graphite. They both slow down neutrons, so they are called moderators. Okay? So, the fuel is enriched uranium. Moderators. Moderators moderate the speed of the neutrons. They slow them down so when they hit the nucleus of the fissionable uranium-235 isotope, it'll split them, and you get 3 more. Okay? All right, so what are the moderators made of? They are made of heavy water, and graphite. So you all know what graphite is. It's what's in the pencils, okay? But I don't think you know what heavy water is. Normal water looks like this. H2O. Heavy water looks like that. H2O. So what's the difference between regular water and heavy water? Well, regular water, the hydrogen is this. The hydrogen is the atomic mass is 1. But in heavy water, the atomic mass of hydrogen is 2. So, heavy water, the isotope of hydrogen is 2, and in regular water, it's 1. And just that extra neutron, because remember, regular water, hydrogen has no neutron, but just that little neutron there makes the water heavy, but it gives us unbelievable properties. The property of heavy water, it gives it 2 properties. One, heavy water slows down the neutrons. It moderates them. And the other property of heavy water is it holds in heat and doesn't boil away, which is unbelievable. So that's heavy water, and most of our reactors use heavy water. And when we get into the making of the atomic bomb, this heavy water production played a super important role. Okay, so we have heavy water and graphite. Those slow down the neutrons. Okay, so we've got the fuel. We have enriched uranium, 3%, uranium-235. Then we have either heavy water or a graphite moderator to slow down the neutrons. Now, the third thing, and one of the most important things in a nuclear core, are called control rods. The control rods go vertically through the core. Remember, all the fuel rods go horizontally, but control rods go vertically through the core, and they can be lifted up or they can be put all the way through. And what the control rods do is what it says. They control the number of neutrons. So, in essence, they control the chain reaction. If you put the control rods all the way through the core, they absorbed all the neutrons and the nuclear reaction stops. If you take the control rods and lift them all out of the core, well, then the chain reaction goes on uncontrolled, and it would be like an atomic bomb explosion. Okay? So, for letter A under control rods. So the control rods control the number of neutrons. So, the control rods control the number of neutrons hitting the uranium-235 nuclei. So, what are control rods made of? The control rods are made of boron or cadmium. So once again, the control rods go vertically through the core. And when these go all the way down, stops the reaction because it absorbs all the neutrons. When you pull them all the way out, well, yeah, you know what happens, an explosion. And we'll tell you more about that when I talk about the Chernobyl disaster. Okay, so now we have what the fuel is, we have what the moderator is to slow down the neutron, we have what the control rods do to either speed up or slow down the chain reaction. The next thing we have to do, number 4, is the coolant. Now, the coolant is like the coolant in cars. It keeps the engine from overheating. Well, the coolant in nuclear reactors keeps the core from getting so hot that it melts down. Okay? And the cool thing about the coolant is the coolant that we use in the United States is this. It's heavy water. So heavy water is not only used as a moderator to slow down the neutrons, it's used as a coolant so the core doesn't melt down. So heavy water can withstand a tremendous amount of heat without boiling and evaporating. Okay? All right, so that is the coolant. So just to give you an idea what the core is like, this is a pretty rough drawing, but you'll get the idea. So there's fuel rods. The little green dots are about 3% uranium-235. So these (3% uranium-235), remember that's called enriched fuel. All around the fuel rods would be moderators. The moderators in our case right now are going to be heavy water. Remember, they slow down the neutrons. Then we have a control rod. It's down this far. It extends way up, and if it came all the way down through the core, it would stop all the neutrons from hitting all uranium-235 nuclei, stop the reaction cold. So that's kind of what it looks like. Now watch. So we have a slow-moving neutron. Let's say it hits that one right there. Okay, so now what happens is 3 fast-moving neutrons come out. There's 1, there's 2, and there's 3. Now, when they go into the moderator, it really slows down. So that one, it slowed it down, but it hit the control rod, so that neutron is absorbed. Now this one slows down, and then it speeds right through, because there's no control rod there. It slows down again, and then it hits that uranium-235 right there, and 3 more neutrons come out. This one does the same thing. The moderator slows it down, then it speeds right through the opening where the control rod is, and then it slows it down again, and then it hits the nucleus, and 3 more come out like that. So that's how a nuclear core works. Whenever a uranium-235 nuclei gets hit, 3 super fast-moving neutrons come out, then the moderator slows them down, then they blast through. If the control rod is up, it goes right through and hits a more moderator, more heavy water, and then it strikes another U-235 once again. If the control rod goes all the way down, then all the neutrons are absorbed. Remember, these control rods are made of boron or cadmium. Okay, so that is how a nuclear core works in a nuclear reactor. Now I'm going to put everything together and draw you a so-so picture of how a nuclear reactor works when everything is all together. Okay, so here's my version of what a nuclear power plant looks like and how it works. First of all, this is the nuclear core right here. The red lines going across this way would be the aluminum tubes with the enriched uranium in them. The blue around them would be the heavy water moderator that slows down the neutrons. Now, these black cylinders, they are the control rods. Okay? Now, watch. This is not only, remember, heavy water is not only the moderator, it's also the coolant. So, and heavy water doesn't boil off. So this water is superheated and it does a pattern, goes up here, down, and around. I only did one side. So as this superheated heavy water comes in here, they bring in river water and they surround this, the heavy water, with river water or lake water. And what that does is this heavy water is so hot that it turns the river or lake water to steam. These things are supposed to be bubbles of steam. So here comes the steam. It goes into the turbine. The turbine creates electricity. The electricity goes out to the power lines and to your home. Now, remember that steam was it was super hot. So as it goes through the turbine, it's still super hot. It condenses into super hot water. So it goes, and I'm sure you've seen these huge towers. They're called cooling towers. And they pump the water up, and they just let it run down the inside of the cooling tower, and hopefully it cools down a lot. And then, if it's not cooled down a lot, they have a canal before they put the water back into the river or lake. Because remember what we said, if the water's too hot, when it goes into the river or lake, it will be void of all oxygen gas, and that means it will kill the fish because the fish breathe dissolved oxygen gas. All right, so that's how this crazy thing works. Okay? Now, what I'm going to tell you is what happened in March of 1979. In March of 1979, I was teaching at Notre Dame High School, and probably very early in the morning, at 3 Mile Island. 3 Mile Island is in Harrisburg, about 150 miles from Elmira. Okay? And it's on an island in the middle of the Susquehanna River. Well, what happened in 1979 is there was a problem with the coolant. Here's a picture of 3 Mile Island in the middle of Susquehanna River, and the reactor building is labeled. That's the one that partially melted down, and you can see the big old cooling towers for the superheated water there. So what happened is, for some reason, a secondary cooling pipe didn't work. And the coolant started to get dangerously hot. The heavy water, dangerously hot. So a relief valve opened. A relief valve opened somewhere here. And it let out a lot of the superheated coolant. But the problem was no fresh coolant came in to take the place of the superheated coolant. So the heavy water level started to drop in the reactor. And as the heavy water dropped in the reactor, it dropped below where some of the fuel rods were. Well, if the fuel rods don't have that heavy water for a coolant, it's just like if an engine doesn't have the coolant in it, it seizes up. Well, that's what happened to some of these rods. They got so hot, they burst. And then it was so hot, it turned some of the heavy water, they split it into oxygen gas and hydrogen gas. This was terrible. So there was a partial meltdown in one of the reactors at 3 Mile Island, plus this whole reactor is encased in this very heavy dome. Well, what happened was there was a huge hydrogen gas bubble in the dome. And they were afraid that, hydrogen gas is explosive. They were afraid that that's what was going to happen. But they eventually got rid of the hydrogen gas. they stopped the partial meltdown, but they told all pregnant women and children they had to evacuate the Harrisburg area. And if the wind was blowing from the south to the north, and we lost that dome and the radioactive steam came up, the cloud would have come up through Williamsport, through Mansfield, Corning, Elmira, and Binghamton, and they said we would have had to been evacuated. Okay? It took about 12 years to clean that up. So my drawing wasn't that great. Let's try the schematic. So number one, cold water intake. That's river or lake water coming in. Number two is where the cold water is going up to the tank, which is in number three. Number three is where the cold water gets converted to steam, and it goes to number four, the turbine. Number five is where the super hot water goes to the cooling tower. Now, on the other side is the nuclear core. Everything in yellow is super hot, heavy water, heated by the core. Notice that the heavy water never comes in contact directly with the cold water from the lake or the river. So what happened at 3 Mile Island is, do you see underneath where it says blockage? There was a blockage. The cold water didn't get up to take the heat away from the superheated heavy water. So the superheated heavy water went back to the core incredibly hot. So there was an escape valve because the pressure was building up, and most of the heavy water started pouring out the escape valve. At this time, the computer was going to open up a couple more cold water valves, but a person that was working at the time closed those valves off by mistake. So the superheated heavy water poured out the escape valve, and it exposed some fuel rods. Well, if you expose the fuel rods, that's it. The fuel rods burst, melted down, superheated the heavy water into hydrogen and oxygen, and that was just about it for 3 Mile Island Reactor 4. Now we're going to talk a little bit about the Chernobyl accident. Chernobyl. This is considered the worst nuclear disaster in the world, ever. Okay? Chernobyl is located in the Ukraine. In 1980, I took a group of high school students to Europe. We started in Prague, and then we went to the Soviet Union. Little did we know when we went to Kiev, it was 80 miles away from one of the worst nuclear disasters ever, but it didn't happen until 1986. We moved on to Moscow. This is what the Chernobyl nuclear power plant looked like before April 26th, early in the morning. It is centered around a small town called Pripyat, which had about 47,000 people in it. The reactor personnel were trying to do a test on one of the reactors. They tested it twice before and it had failed. So they were putting the control rods all the way down, which means that all the neutrons were being absorbed and the reactor's reaction was just about finished. Well, there was a problem. The problem was the reactor's design was pretty lousy and the test was taking too long, so there was a shift change, and the people coming in didn't really know what the heck the test was all about. So this is where the bad things started to happen. So they put the control rods all the way down through the reactor. Now don't forget, control rods control the number of neutrons coming out, hitting more fissionable uranium-235. So if all the control rods were down, that means everything, all the neutrons were absorbed and the reaction was just about ready to shut down. So the new group of people at the control were freaked out about the reactor shutting off, so they pulled all the control rods, all 211 of them, which were 21 feet tall, all of them out of the graphite. So you can imagine what happened next. There were no control rods to control the number of neutrons, so the reaction zoomed way up high and a controlled reaction turned into an uncontrolled chain reaction, kind of like an atomic bomb. And that's when the reactor blew up. This is a picture of what the bomb blast would have looked like when the nuclear reactor exploded. It would have been just like an explosion of an atomic bomb. And this was the result of what the building looked like. Completely blew off the top and all the sides. And the part that really blows me away is there was more radioactive material spewed out into the atmosphere than both of the atomic bombs that were dropped on Japan. I just can't imagine that. And you also have to remember it wasn't just radioactive particles spewing out. There were at least 300 tons of graphite, which was the moderator, blown out of the building and went all over the grounds because the graphite slowed down the neutrons, and in it, it had the control rods and the fuel rods. In the morning after the explosion, the town of Pripyat was totally abandoned. It took 1,200 buses and 200 trucks to move 47,000 of its inhabitants. One suitcase, no pets. They haven't been back. This happened in 1986. 2 days later, 1,500 miles away in Sweden, the radiation alarms went off. Nobody knew what was happening. They may have thought it was a nuclear Russian sub that had blown up. They had no clue, so we sent some planes over. They were called radiation sniffers. We got up in the atmosphere with the planes, and they found out the radiation was coming from southeast, and then they knew it was coming from the Soviet Union. The Soviets didn't tell the world that there was an explosion in a nuclear reactor until several days later. And on this map, you can see that radiation went all over, to France, to Germany, to Italy, to the Scandinavian countries. It went everywhere. The majority of the radioactive particles that were coming out of the blown up reactor 4 for 10 full days, most of it was radioactive isotope 131 with an 8-day half-life, and worse, cesium-137 with a 30-year half-life. That is why most of the people around Europe and the Soviet Union and Scandinavia were popping tons of iodine pills so that would fill up their thyroid gland so the radioactive iodine-131 wouldn't be able to get in and cause problems. One of the first things that the Soviets did to try to stop the flow of radioactivity coming out of the core was to take helicopters and dump about 5,000 tons of neutron-absorbing material like boron and cadmium into the hole to try to stop the nuclear reaction from occurring. After the reactor blew up that night, the first people on the scene were the firemen, and they had to try to put out the fires that were caused by the graphite and the radiation from the uranium fuel. They had no idea what they were in for. The majority of the firefighters died within several days because of the amount of beta particles that hit them. Remember, we talked about a nuclear suntan. Their skin turned black, lips black, and then the majority of them died. This is a picture of the remains of Reactor 4 and its building taken from Reactor 3 rooftop. Now, remember, burning graphite with fuel rods embedded are all over the area. And the next picture you're going to see is the men that had to try to sweep off the buildings and dump the burning graphite back into that hole. At first, the Soviets borrowed some robots from Germany and Japan to try to push the burning graphite with fuel rods in it into the hole, but the radiation was so strong it wiped them out. So guess what they used? Yep, they were called human liquidators from the Soviet army. They really had no idea what they were in for. They could only work for 40 seconds. Then they had to run back into the building. They had to make their own protection. This is a little lead-lined vest that this guy is wearing. They didn't know what was going on, and this guy put metal lead on his head. Remember, they only could work for about 40 seconds. Here's a picture of them on the roof trying to push all the graphite that is burning and the radioactive waste back into the hole. Yeah, I really didn't envy these guys. That was a tough, tough job. Many of them came down with radiation sickness. This is a picture of the initial exclusion zone, which was about 320 square miles and about 50,000 people. This was later pumped up to 1,600 square miles, and at least 350,000 people were displaced from this zone of exclusion. And some people actually snuck back and started to live there again. The things they did to keep the radiation in was astounding. Here's a bulldozer. They bulldozed quite a few villages, and they pushed down all the buildings and all the trees, and they buried all the buildings and all the trees in the contaminated zone. So after all the bulldozers bulldozed all the villages into the ground, and the trucks and buses carried the people from Pripyat to someplace else, and all the helicopters that were dumping the neutron-absorbing metals into the radiation and reactor hole, this is where they all were. They're all left in a boneyard because all these trucks, over 2,000 trucks, planes, and everything else, are too radioactive to come back into service. This is what the control center of Chernobyl looks like today. It's had its day. Now, when this explosion occurred, there was so much radiation in the air that it actually turned all the trees and leaves red. So this is called the red forest. Everything died eventually. This is a classroom in a school close to the reactor. These are dead fish caused by radiation that jumped out of the lake, amazingly enough. And this is what the town of Pripyat looks like now. It is a virtual ghost town. So let's talk about the human suffering from this disaster. Between 200,000 and 1 million abortions were performed around the areas because of the intense radiation could have caused abnormal babies to be born. The bone cancer, thyroid cancer, and blood cancers were astronomical in the area. So this is what the abandoned city of Pripyat looks like now. That big dome you see in the background is what is covering Reactor 4. So they have encased it, and they also put cement underneath, and they plasticized all the ground around it so the wind can't raise the radioactive dust. So believe it or not, you can now take tours to Chernobyl if you are into getting radiated. So it says tourists flock to Chernobyl. Yeah, that's nice. There's no way I would go there. Here's a few pictures of the amusement park that was abandoned in Pripyat.